Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Satya Naseem. On behalf of Garrison Academy Senior Campus, welcome you all in APSEX online support program. This is week 3, day 1 of our chemistry lesson for class first year. Students, we will start with unit number 2, atomic structure. As far as your board paper is concerned, this chapter is very important. The objective of today's lesson are you will be able to understand the discoveries of cathode rays and its properties. You will be able to understand the measurement of charge to mass ratio. You will be able to understand Millikan's oil drop experiment. Students, let's start the first topic, 2.1, discharge tube experiment. According to Dalton, an atom is the simplest unit. It is a compact body, that is, it is highly dense. But the discoveries in the later half of the 19th century have modified the Dalton's concept about the atom. According to these discoveries, an atom is a complex unit consisting of 100 particles. Out of these particles, electrons, protons, and neutrons are the most important, and they are all time present in an atom. Students, let's understand the instrumentation of a discharge tube. This is a gas discharge tube. It is also known as a cathode ray tube or an electric discharge tube. It is made up of glass. Two metallic electrodes, that is cathode and anode, are fitted with this tube. The tube is filled with any gas, air, or vapor of any substance. The electrodes are connected to a source of high voltage. Cathode is connected to the negative terminal of the battery and anode is connected to the positive terminal of the battery. A vacuum pump is attached to this tube. This vacuum pump is used to adjust the pressure of the gas, air, or vapor which is present in the discharge tube. With the help of vacuum pump, we can remove the gas from the discharge tube and the pressure of the gas can be adjusted accordingly. When the gas is removed, then the pressure of the gas inside the gas discharge tube becomes low. Students, let's understand the working of the discharge tube. The discharge tube experiment is actually related to the discovery of electrons, or we can say that it is the experiment which is related to the discovery of cathode rays. In the beginning of the experiment, the electric current was passed through a gas. The electric current was passed through a gas. The gas was adjusted at a pressure of 760 torr, it is an ordinary pressure, and a voltage of 5000 volt was applied across the electrodes. It was seen that the gas inside the discharge tube remained unaffected. There was no effect. When the pressure was reduced to 4 torr with the help of vacuum pump, it was observed that a glow was seen in a discharge tube. When the pressure was further reduced to 0.01 torr and a high voltage of 5000 to 10,000 volt was applied across the electrode, the original glow disappeared and light was produced in the discharge tube, as we can see from this picture. Then, in this case, the gas becomes a conductor. When the pressure is lowered to 0.01 torr, the gas became a conductor. The electric discharge took place through the gas. The electricity was passed through the gas. When the pressure was further reduced, then the emission of light was ceased. Now, when the pressure was further reduced, no light was seen, but certain rays were observed, and these rays are known as cathode rays. These rays originated from cathode and they travel towards the anode. That is why these rays are known as cathode rays, because they originated from cathode. And this discharge tube is also known as a cathode ray tube. It is also known as a gas discharge tube because the electric discharge, the passage of electricity takes place through the gas in this tube. It is also known as the electric discharge tube because the electricity is passed through a gas in this tube. The modern example of gas discharge tube is neon sign. In neon sign, neon gas is used. So, what were the conclusions? J.J. Thomson was the first scientist who identified the cathode rays. Actually, These cathode rays are the electrons that are negatively charged, and these electrons move towards the positively charged anode. So J.J. Thomson was the first scientist who first identified the electrons in the cathode ray tube in 1887. After J.J. Thomson, Faraday and Crook also studied what is the effect of passing electric current through a gas in a discharge tube. As a result, the subatomic particle with a negative charge, that is electron, was discovered in a gas discharge tube. Cathode rays are basically the electrons that travel from cathode towards the positively charged anode. Students, let's discuss about the main subatomic particles of an atom. The subatomic particles of an atom are electron, proton, and neutron. These particles are also known as the elementary particles or the fundamental particles. Why? Because these particles are present in all the atoms. They are building block of all the atoms, and the characteristic of atom depends upon these particles. That is why these particles are known as the elementary particles or the fundamental particles. Some other particles are also present, such as neutrino, antineutrino, positron, pions, and muons, but these particles are short-lived, they are unstable, and they just exist for few seconds only. So let's discuss the history of fundamental particles of atom. Electrons were discovered by J.J. Thomson in 1887. The name electron was given by Stoney in 1886. Protons were discovered by Goldstein in 1886. The name proton was given by Rutherford. Neutrons were discovered by James Chadwick in 1932. Students, let's study the properties of cathode rays, that is the properties of the rays that are produced in a gas discharge tube. The first property is the effect of magnetic and electric field. In the first diagram, we can see that when a magnet is brought close to the cathode rays, then the cathode rays are deflected towards the north pole. North pole is positively charged and south pole is negatively charged, and that is why the cathode rays are deflected towards the north pole of the magnet. It means the cathode rays are deflected in a magnetic field, and it is very clear from this picture that the cathode rays are deflected in a magnetic field. This deflection was studied by J. Perrin in 1895. And if an electric field is brought close to the cathode rays, then the cathode rays are deflected towards a positively charged electric plate. Means cathode rays are negatively charged, and that is why they are deflected towards the positively charged electric plate, showing that the cathode rays are negatively charged. So this deflection was observed by the scientist of those times, and J.J. Thomson proved that these rays always travel towards the anode because these cathode rays are negatively charged, and they always move, or they are always deflected towards anode because anode is a positively charged plate. So it was proved by J.J. Thomson in 1897 that the cathode rays are negatively charged because they are deflected towards the anode. The cathode rays, on striking the wall of the glass tube, produce a green fluorescence. We can see a green fluorescence, a green glow, and this green glow is produced when the cathode rays strike the wall of the glass tube. Let's study the second property, that is straight line motion. This is an experiment which was performed by Hittorf in 1869. This is a cathode, this is an anode. This is an opaque object which is placed in the path of cathode rays, and this is a fluorescent screen. The fluorescent screen is a screen that glows when the rays strike on this screen. The cathode rays originate from cathode and move towards anode, and when these cathode rays falls on an opaque object, then the shadow of an opaque object is casted on a fluorescent screen. This experiment was performed by Hittorf in 1869, and this experiment proves that the cathode rays always travel in a straight line perpendicular to the cathode, and when they strike an opaque object, they cast a shadow on the fluorescent screen. So cathode rays have a straight line motion. Let's study the next property, that is material particles. Cathode rays are material particles. Students, in this picture we can see the shadow of an opaque object which is casted on a fluorescent screen. So cathode rays are material particles. In this experiment, a paddle wheel is placed in the path of cathode rays. When the cathode rays strike this wheel, the cathode rays drive the wheel. The cathode rays can move this paddle wheel. So we can say that the cathode rays are material particles because they can move a matter, that is a paddle wheel. Paddle wheel is made up of glass, for example, and the cathode rays have a tendency to drive this wheel. So cathode rays are material particles because they can move a matter, that is a paddle wheel, and the cathode rays possess momentum, that is cathode rays have a mass. These rays possess some velocity, means these rays have some momentum, and they are material particles because they can move a matter. Let's study the next property, that is X-ray production. When the anode metal is of large atomic mass and when the cathode rays fall on the anode metal of large atomic mass, then X-rays are produced, means cathode rays are capable of producing X-rays when the anode metal is of large atomic mass. Students, this picture shows the setup in which a paddle wheel is used. Heating effect. Heating effect can be seen in this picture. This is the center. In the center we can see a platinum foil, and when the cathode rays fall on this platinum foil, they produce heat on this foil, and the heat begins and the platinum foil begins to glow. A red glow is seen on this platinum foil. Ionization. They can ionize gases, means the cathode rays, when strike the gas particles which is present in the discharge tube, they knock out electrons of the gas, and the gas particles are converted into a positively charged ion. So we can say that cathode rays can ionize gases because when the cathode rays strike the gas particles which is present in the discharge tube, the cathode rays knock out electrons which are present in the gas, and the gas particles are converted into a positively charged ion. So we can say that the cathode rays can ionize gases. Chemical effect. They can cause a chemical change, they can cause a chemical reaction in any material on which they fall, means they can add electrons. They have reducing nature. They can add electrons in any material on which they fall, and in this way a chemical change or a chemical reaction takes place. Penetration. They are capable of penetrating in the metallic sheets like aluminium or gold. They have a good penetration power. So what were the conclusions? J.J. Thomson determined the charge to mass ratio of an electron, that is cathode ray. J.J. Thomson was unable to determine the charge or the mass of the electron independently, but he was able to determine the charge to mass ratio of an electron, and the value of charge to mass ratio is 1.7588 into 10 raised to power 11 coulombs per kg. This is the value of charge to mass ratio of an electron, and whatever gas or vapor you use in a discharge tube, you can use any gas, any vapor in a discharge tube, the cathode rays and the electrons will always remain the same. The nature of cathode rays and electron will not change whatever gas or vapor you use in the discharge tube. It means that it proves that the electrons are present in all the atoms, because if you use any gas or any vapor, the electrons and the cathode rays are always same. So J.J. Thomson concluded that all atoms contain electrons. Let's students study the measurement of charge to mass ratio. This experiment was performed by J.J. Thomson. He measured charge to mass ratio of an electron, that is cathode ray, and this experiment is known as J.J. Thomson cathode ray experiment, and this experiment was performed in 1897. Let's understand the instrumentation of this experiment. In this experiment, this is the cathode, this is anode, this is a magnet. A magnet is used to create a magnetic field. This is electrically charged plate, which is negatively charged, and this is a positively charged plate. These plates are used to create an electric field. This is a fluorescent screen. This is point A on the screen, this is point B, and this is point C. So J.J. Thomson studied what happens to the beam of cathode rays in the magnetic field and in the electrical field. Actually, J.J. Thomson was studying the effect of magnetic field and electrical field on the cathode rays. In the beginning, the magnetic field and electrical field is not applied, means the magnetic field and the electrical field is absent. We can see that the cathode rays strike at point B. No deflection is seen in cathode rays when the magnetic field and the electrical field is off. Then, when only electrical field is applied, the magnetic field is off, only the electrical field is applied, then we can see that the cathode rays are deflected and they strike at point A. Why? Because the cathode rays always move towards a positively charged electric plate. So the deflection was towards the positively charged electric plate, and the electron strike at point A when the electric field is on. Now when the electric field is off and magnetic field is on, that is magnetic field is applied, then we can see that the electrons strike at point C, that is the cathode rays move towards the positive pole of the magnet, that is the north pole, and the electrons strike at point C. Now both the fields are on, both the magnetic field and the electric field is on, and the strength of these two fields is adjusted in such a way that the electron strike at point B. The deflection is neither towards the point A, neither towards the point C. The electrons strike at point B. So what were the conclusions? From the comparison of the strength of electric and magnetic field, charge to mass ratio is calculated. We compare the strength of both the fields and we calculate the charge to mass ratio of an electron. The calculated value of charge to mass ratio is 1.7588 into 10 to the power 11 coulombs per kg. It means 1 kg, the charge on 1 kg electron is 1.7588 into 10 to the power 11 coulombs.